Hello everyone, in this video I shall be discussing the physics problem of vertical circular motion of a particle considering surface friction. Let me first read out the problem statement for you. A particle is imparted a horizontal velocity u at the bottommost position of a vertical semicircular track of radius r. The kinetic friction coefficient for the particle and surface pair is mu. Find the minimum value of u required for the particle to complete the vertical circle. The figure corresponding to the problem has also been shown, so let's start with the solution. We know that because the track is circular, the particle will follow its locus and execute a circular trajectory. And when a particle follows a circular path, that is exhibits circular motion, we work in terms of radial and tangential directions. The first step is to draw the free body diagram of the particle at a general position. What's a general position? A general position is a position attained in some time t, and during this time the particle has moved angularly by an amount theta. It has covered a distance along the periphery of the track, that is a circumferential distance of s, will denoted by small s, and at the current moment it has a net speed v. The magnitude of its current velocity vector is v, and this velocity vector is along the tangent to the particle as shown. This position is called the particle's general position, and we have to identify the various force vectors acting on it at this position and draw them pictorially. This pictorial representation will be called the free body diagram of the particle at this general position. So in our case, we have three forces acting on the particle at the general position. They are the normal reaction from the surface, the particle's weight, and the kinetic friction force. The normal reaction from any surface acts along the local normal, and in case of a circular path, rather a circular surface, the local normal is directed along the radial direction. Since the particle is on the concave side of the surface, the normal reaction will be directed radially toward the center. The second force is particle's weight, mg, the product of its mass and the acceleration due to gravity on the surface. It will act vertically downward. And third force is kinetic friction force. This will act opposite to the particle's instantaneous velocity vector. So it will act in our case along the downward tangent, and its magnitude is mu n, product of the kinetic friction coefficient and the instantaneous normal reaction. That completes the free body diagram. Next step is to use the Newton's second law of motion at the general position. Newton's second law for a particle is F net vector is m times a vector. The net force vector acting on the particle at any instant is the product of its mass and its instantaneous acceleration vector. This is a vector equation. We'll be needing to use it. Uh, will we have to break it down into components and use it along various directions. In case of circular motion, we resolve various forces acting on the particle along the radial and tangential directions. So our topmost equation here can be broken down further into two equations. Along the radial direction, we have Fr net is m times ar. The net radial force is equal to mass times radial acceleration. And along the tangential direction, we have Ft net is m into at. The net tangential force is product of mass and tangential acceleration. In the radial direction, the forces acting toward the center will be taken positive, and ones acting opposite to it will be away from the center will be taken as negative. In the tangential direction, the forces are acting along that tangent which is aligned with the particle's velocity, direction of motion, its velocity vector will be taken as positive, and those opposite to it will be taken as negative. Also, by definition, the radial acceleration at any instant is v square over r, where v is the particle's speed, and tangential acceleration is dv by dt, the rate of change of speed of the particle with time. By speed, we mean the magnitude of its velocity vector. So in our case, the radial and tangential force equations become n minus mg cos theta is mv square upon r, and minus mg sin theta minus mu n is m times dv by dt. We now have to solve these two equations for the unknowns. So let me write down these equations once before we start with the solution. we have two equations, and how many unknowns do we have? That is also two. One unknown is the particle speed v as a function of either time or location theta. The other is normal reaction, which is also either a function of time or a function of theta, whichever can be obtained. So we need to solve for two unknown functions. Two equations and two variables. So the way to go is to eliminate one of the variables, then solve for the remaining one. When we have one equation, one variable, and after having obtained it, we can then go back to the other equation to find the eliminated variable as well. So in our case, it's easy to eliminate n. I can simply feed it from the first equation into the second one. Let's do it. Minus mg sine theta minus mu times mg cosine theta plus mv square over r is m times dv over dt. This yields me this can be simplified as dv by dt is minus mu v square over r minus g times sine theta plus mu cos theta. Now we have one equation and one variable, which is v. N has been eliminated, and this is a differential equation rather than ordinary differential equation. But notice that it cannot be solved in its current form, because for an ordinary differential equation to allow a solution, it needs to have only two variables, one dependent and one independent, and all other parameters appearing in the equation need to be constants with respect to these variables, which isn't the case here. We have three variables here. One is v, the speed, next is time t, and third is the theta. As the particle progresses in its motion, all these three variables keep changing. So we cannot solve it in the current form. So what we're going to do is we're going to modify it. We're going to make use of the fact that the tangential acceleration, which by definition is dv over dt, it can also be written as v dv over ds. S here is the distance traveled by the particle along the circumference during its journey from the initial instant to the general position, and during this time it has covered an angle theta, right? So how does this expression arise? What we do is we multiply and divide dv over dt by ds so that it remains unchanged, and now we can reshuffle the two differentials in the denominator. I can bring ds here and dt here. Now ds by dt, the rate at which this distance is covered, is by definition the speed of the particle at the current moment. So we can write this as dv upon ds times v. Hence we obtain this expression, this one. Furthermore, we know that in case of circular motion, the distance along the arc length and the corresponding angles obtained at the center are related as s is equal to r times theta. Now if I take differentials on both sides, I get ds is d of r theta, and since r is a constant, I can factor it out. This becomes r times d theta. Therefore, I can write ds as r times d theta. So my tangential acceleration can be written as v d over r times d theta. Now if I use this form, then our differential equation is solvable. Let me write it down. Now this is a differential equation to be solved in v as a function of theta. V is the dependent variable and theta is the independent variable. In this form it is solvable. So let's obtain the solution. We need to use a change of variable and little bit of uh, integration. Let's write down the equation once again. It's v dv over theta over d theta is minus mu v square minus rg times sine theta plus mu cosine theta. I've taken the capital R on the other side. So first of all, we'll be using a change of variable. Let v square equal to b, let's say p. Taking differentials on both sides, we get d of v square is d of p, and using the chain rule, d of v square is 2v times dv. This is equals to dp. Therefore, v dv becomes dp over 2. This implies our equation becomes dp over 2 d theta is minus mu p minus rg times sine theta is mu cosine theta. So we get dp over d theta plus 2 mu p is minus 2 rg times sine theta plus mu cosine theta. Now this equation that we obtained here is a first order linear differential equation, and it has a standard solution which is obtained by the integrating factor technique. Let me write it down here. Dy over dx plus y times p of x, where p is a function of x, equal to q of x, where q is also a function of x, is a standard first order linear ordinary differential equation with the solution. Excuse me just for a moment. This is the standard solution is y into if is integral of qx multiplied by if plus c being an unknown constant of integration, and if being the integrating factor for this equation, which is e to the power integral of px dx. If we compare this equation with ours, we can say that integrating factor for our equation is e to the power integral 2 mu times theta, which is 2 mu e to the power 2 mu times integral d theta. 2 mu is a constant, it factors out, so e to the power 2 mu theta. Therefore, the general solution to my equation can be written as, using the solution to the standard first order linear ordinary differential equation that I mentioned on the right side. Referring to it, we can say that solution to our equation is p times e to the power 2 mu theta is integral of minus 2 rg times sine theta plus mu 2 plus mu cos theta d theta plus c. And since minus 2 rg is a constant, I can factor it out of the integral. So I can write this as minus 2 rg integral of, oh wait, I forgot the integrating factor term. We also have e to the power 2 mu theta here. Yeah. Integral of this plus c, where c is an unknown constant of integration. So to proceed ahead now, we have to evaluate the right hand integral appearing on the right hand side of our equation. This integral can be obtained by the technique known as integration by parts. I'll write down the expression of the evolved integral and won't go into the details of how we obtained it. You can refer integration by parts for it. So this integral is e to the power 2 mu theta times 3 mu sine theta plus 2 mu square minus 1 cosine theta divided by 1 plus 4 mu square. So my solution becomes P times e to the power 2 mu theta. Let me write it down here. Is equal to negative 2 rg times this integral plus c. Now if I divide throughout by e to the power negative 2 mu theta and also replace p by v square, I get v square is minus 2 rg divided by 1 plus 4 mu square times 3 mu sine theta plus 2 mu square minus 1 times cosine theta plus c e to the power negative 2 mu theta, where c is an unknown constant of integration. Now this constant can be obtained by the initial condition, which is that when the motion began and zero angle was covered, the velocity was the velocity given as u. So value of v, the initial condition we have is v at theta equal to 0 degree is u. So let's use it. We get u square is minus 2 rg over 1 plus 4 mu square times 2 mu square minus 1 plus c. Therefore, c can be written as u square plus 2 rg upon 1 plus 4 mu square times 2 mu square minus 1. So our final solution becomes v square is negative 2 rg over 1 plus 4 mu square bracket 3 mu sine theta plus 2 mu square minus 1 times cosine theta plus c, which is u square plus 2 rg upon 1 plus 4 mu square times 2 mu square minus 1, and c is multiplied by e to the power minus 2 mu theta. So this is one term and this is another term. That completes our expression for v as a function of theta. And recall we had two unknowns. The other one was n. So after obtaining, we had eliminated n. We have now obtained the other variable v. How can we obtain our first variable n? Using the equation by which we eliminated it. We used n is equals to mg cos theta plus mv square by r and fed it into the tangential force equation. So I have got v square, I can feed it here, I will then get my normal reaction as a function of theta. Let's use it. N is mg cos theta plus mv square by r. So n will be mg cos theta plus mv square by r. So this entire equation will be, right hand side of the above equation will be multiplied by m over r and we'll add it to mg cos theta. So this will be minus 2 mg upon 1 plus 4 mu square bracket 3 mu sine theta plus 2 mu square minus 1 times cosine theta plus m over r u square is 2 mg 1 plus 4 mu square times 2 mu square minus 1 whole multiplied by e to the power negative 2 mu theta. This is the second unknown which we had headed to search, and this is the first one. we had to find the what we were asked to find was the value of u for which the particle completes the vertical circle. Now we know that the condition for a particle to complete vertical circular motion is that the value of normal reaction at the topmost position must be greater than equal to 0. So in our case, this translates to n at theta equals to pi, that is 180 degrees, must be greater than equal to 0. So we go to the expression of n, put theta as pi, and that value is set to be equal greater than or equal to 0. So let's do it. Mg at theta equal to pi, or n will become mg cos pi. Cos pi is -1, so minus mg minus 2 mg over 1 plus 4 mu square square bracket sin pi 0 and cos pi is -1, so again we get -1 2 mu square minus 1 plus square bracket mu square over r plus 2 mg times 2 mu square minus 1 by 1 plus 4 mu square times e to the power -2 mu pi. This must be greater than equal to 0. And from this inequality, we can now find out the value of u, that is the minimum value of u. So we get mu square by r plus 2 mg times 2 mu square minus 1 over 1 plus 4 mu square times e to the power -2 mu pi is greater than equal to mg plus 2 mg times 2 mu square minus 1 over 1 plus 4 mu square. If I multiply throughout by e to the power 2 mu pi, I'll get e to the power 2 mu pi here, and this will be gone. And then if I take this term on the other side, I get mu square upon r is greater than equal to mg e to the power, let's open the bracket on the right side, mg times e to the power 2 mu pi plus 2 mg 2 mu square minus 1 over 1 plus 4 mu square factored out e to the power 2 mu pi minus 1. If I multiply throughout by r over m, I get here u square, and here I get m cancels out, I get rg, and even here I get rg. So my finally I get u is greater than equal to rg e to the power 2 mu pi plus 2 rg times 2 mu square minus 1 over 1 plus 4 mu square times e to the power 2 mu pi minus 1, and square root of this entire thing. So this is the expression that would be our solution. This is the minimum value of u on the right. U is greater than equal to the right hand side. So the right hand side expression is the minimum value of u that is required to for the completion of the vertical circle. And one can verify that for mu equal to 0, that is without any surface friction, this minimum value of u, the expression for it, reduces to the familiar expression under root 5gr. that could serve as an additional step for verification, although it's not, you can say, a perfectly, you cannot say it's a proof of the solution to check it, but it certainly uh, adds to the accuracy. So I hope this helps. In the next video, we'll see another unique physics problem. Thank you.